Hey everybody, welcome to our SAT office hour. So tonight we're going to focus on statistical analysis. Um, but before that, let's get started on our challenge problems. So the first weekly challenge problem, we could do this several ways. We could choose values for A and B. We could use Desmos. We could just plug in the answers. The way that I'm going to do it is actually by factoring. So if we want to know where these are equal to each other, we're simply just going to have ax plus b equals ax squared plus bx. And then I want to get everything to one side. So I'm going to have 0 equals ax squared plus bx. And then I'm going to subtract the ax and subtract the b. And whenever you have four terms, what you want to do is you want to factor by grouping. So out of the first two, I can take out an x and I get ax plus b. And out of the second two, I can take out a -1 and then I also get ax plus b. Well, that's good because now I know my factor by grouping is going to work because I have the exact same thing in the parentheses. So I have x minus 1 times ax plus b. And then, as you always solve quadratics, you set them factors equal to 0. So one of the answers is 1 here, so that gets rid of these two. And then the other answer, if I do ax plus b equal to 0, I get ax equals negative b, and x is negative b over a. And that is answer choice D. Like I said, you could just go start plugging in the answers. Like if you plug in 1, you'll see here you'll get a plus b, and here you'll get a plus b. And then if you plug in negative b over a, then you will get the same thing. But this was just a nice way to review some factoring. It's probably the way I would do it anyway, because I feel like if you are good at factoring, you can do this pretty quickly. All right. Now, number two. Here we have one that's really, really good for Desmos. What it means for a line to be tangent to a circle is when it goes through the circle or it intersects the circle at exactly 1 point. Oh, excuse me. So, um, what we're going to do is we're just going to graph these, make a slider, plug in these values for the slider, and see which one intersects the circle exactly at 1 point. So let's jump to Desmos here. And the first thing I'm going to do is I'm going to put in the y equals 2x minus 5. And then I'm going to put in the x squared plus y squared equals r squared. And then I'm going to make it a slider. And then I don't use the actual slider. I just type in the answer. So if I type in 2, that's answer choice A, I see that the line does not intersect the circle. So therefore, I know that that's not the answer because again, I want it to be tangent. Then I'm going to do the next one, which is square root 5. That looks like it does. So I can assume that's the answer. But if you're not convinced, this one intersects twice. And then just 5 intersects twice as well. So I'll go back to square root 5 so we can see again that it intersects at 1 point. And so that is the answer. So we get square root 5. All right, so I think that's a good one to just, you could do it really quickly in Desmos. So that's why I chose to do it that way. Okay, let's move on to tonight's lesson, where we're going to do a lot of reviewing or maybe teaching of some statistical concepts that they like to ask on the SAT. So we've got everybody has to pass this driver's test. They offered a new program where the students could attend an additional review. Those that attended additional review scored higher. And the thing is, the students had a choice. This is called volunteer bias. Not that you need to know that necessarily, but the idea is if you ever have a situation where it's not done randomly, then there is nothing that you can assume from it. Because who's to say that the people that attended the review, like they're the type of people that were going to study and do better anyway. All right. So the people who didn't attend it. Now, if they split the group up and then 50% of the people went and 50% didn't, and with if it was done randomly, then the 50% who did and who didn't, they would be a nice mix of all the different types of people, some that study, some that don't. So then you'd be more likely to say that the review worked. But there's no way we can say that it worked. Again, you don't even need to get into it as much as I am, honestly. If they do not mention the word random, then there is no kind of conclusion that can be made. So if this is a random assignment of an experiment, but if it's not a random sample, or in this case, it's not people aren't assigned randomly to a group, then we cannot, there's too many what are called confounding variables. All right. So really, really look for the word random. And if you don't see it, then you can assume that it's the answer that's like that you can't conclude anything. Okay, number two. Number two is a nice kind of review of what margin of error is. So it says that we're trying to conduct a study to find out the percentage of people in a town who prefer online shopping over in-store shopping. So it's really important to understand that there's no way to actually answer this question unless we could ask every person in a town, which is just not feasible. So we're in search of something that we can't find. So we just try to get really, really good estimates. So we want to know what percentage of people. So they got a study indicated this. So they got some sample where 75% of the people preferred online shopping and a margin of error of 0.04. So what that means, or 4%. So that means that it's very likely that the actual percentage of people who prefer online shopping, which again is something we could never find, but we're very sure that it's within 4% of 75%. All right, so if you start at 75%, we go 4% this way, that's 71%. And you go 4% this way, that's 79%. So it's likely, right? So not definitely, but it's likely that it's between those values. So that's D. All right, so that's what margin of error is. We're trying to, in these types of problems, predict something um, in a very accurate way, but we can never say with 100% what it is because it's not something that can be found unless we could ask every person in the population, and then if we could, we wouldn't be doing the statistics to begin with. We would just figure out the answer. All right, so it's all about there's always some sort of error involved, and that's what margin of error actually means. Okay, so we'll talk about that more. So now we look at number three. So these types of problems, which of the following is the largest population from which the results can be generalized? So here is where there needs to be a random sample, and there is. So we're all good. We're all good with the whole random part. And it depends on where the sample was taken from. So we start with a population of people. And then we take a sample from that population. A random sample means that every single person in the population has the same likelihood of being in the sample. So the sample becomes like a smaller version of the population that we can then generalize results. So you take a sample, and then from the sample, you generalize. I'm going to run out of room here, but you generalize something about the population. Well, you can only generalize about the population that the sample has been taken from. So that is the most important part of these problems is to read carefully. You can kind of skim group survey to random sample of teachers from boom. This is where I really, really start to pay attention. I've just been kind of skimming and then now from one of the school districts in the state. So the random sample, that's the population. This is the population. The one of the school districts in the state. And my bad, math teachers. Okay. So not even all teachers. So only math teachers in the school district, in a specific school district, are the population. So all math teachers in the school district, and that is our answer. So all teachers, nope, they only math teachers were part of this population. All math teachers in the state, nope, only the one school district and the teachers in the sample. Well, that is true. Any sample, you can always generalize to the sample because the sample is itself. But that is not what's that's not the largest population. The population is bigger than the sample. So the sample itself, um, that would be the answer if it wasn't randomly done. If something's not randomly done, then the information you get from a sample only applies to the sample. So you can only apply it to a population if it's randomly done, and if it is, the population that it's taken from is the only thing that you can generalize the results to. All right. Let's keep moving. So we take a look at this one, and we have another similar problem. The largest group, I would always read the question first. It's just kind of a habit of not wanting to read all this. So, what is the largest group to which the above conclusion can be generalized? All right. So now I go back and I say, all right, company offers blah, blah, blah. Okay. The head of the sales department was interested in determining if the employees in her department liked complimentary coffee. Okay, here we go. She selected 175 random. Okay, so we're good. Check on the random from her department. Okay, so the employees were selected from her department. Okay, and she is in the sales department. Okay, so only the sales department here is the population. We can't project to anything else or generalize to anything else. So the 175 who were asked, it definitely can be generalized to them, but that's not the largest group. 44% of the employees at the company. That doesn't, not the whole company, because we only took it from the sales department. All employees at the company, again, doesn't really make sense. So it's got to be D because the sales department, all the employees in the sales department, that's where the random sample came from. So wherever we collect the random sample from, that is what the results can be generalized to. Okay. All right, number five. So we have this one is plausible value for the total number of people in the population who support something. Okay. So we have a population of 15,000. So that's what we're interested in. And it's estimated that 27% of them support something. Again, don't really care what it is. And there's a margin of error of 4%. So again, that means 27% in this like sample did. And we figured out that there's a 4% margin of error. So 4% this way is 23%, and 4% this way is 31%. Right? So I went 4% in this direction and 4% in this direction. So it's likely that the number of people in the population who support the taxes is between 23% and 31%. But again, it's of the population. So you can easily just find 23% of 15,000. So that's just 0.23 times 15,000 is 3450. And then 31% of 15,000 is 4650. So again, 0.31. And the only answer that's between this is this. Honestly, in some of these, you could do this to be safe, but if I just did 27% of the population, that gives me 4,050. And the only answer that's the closest answer to that is C. You could probably get away with that. But again, I'd rather us like really understand what's going on here. So again, it's likely that this percentage of the population um, are going to vote in favor of this. So again, the only number that's between these two numbers is 3750. And these numbers don't make sense. These numbers are based off of the sample. That's not what this is. We're trying to number of people in the population, so the percentages are applied to the 15,000. All right, moving on to number six. So here it says which of the following is likely true. Okay, that doesn't really help me. So if I just kind of skim this, we got some companies. They all they do is that company A used a sample size of 730 and company B used a sample size of 430. Okay. So my guess is when they only talk about sample size, that it's going to be some kind of question about margin of error. So here's how it works. This is a type of question that they like to ask about margin of error. So the margin of error is how off we are, how likely we are off from whatever our sample value was, whether it's a mean or a proportion. So if we have a larger sample, the bigger the sample, the less the error that we're going to have. All right. So the more data we collect, the more accurate our results are, is kind of how you can look at it. Or if you look at an extreme, if you wanted to find out, who's in favor of voting in favor of this thing, and you ask like three people and two of them are in favor, I think we all realize that it'd be unlikely to just assume that two-thirds of the whole population, because you only ask three people, is it's going to project out. But if you ask 600 people, right now your results feel much more likely than if you only ask like two or three people. All right. So when sample size goes up, margin of error goes down. All right, that's the whole point of this problem. So the proportion will be smaller. Well, A and B are talking about the proportions. We don't know that. We don't know what the proportions would be. Um, so it really comes down to C and D. The margin of error associated with A will be smaller. So yes, that's true because A has a bigger sample size. So and again, it's important that it is coming from the same population, right? If these were just completely different populations, then we wouldn't be able to say this. But within the same population, if you increase sample size, you're going to lower margin of error. And the D is just saying the opposite of that. All right. So bigger sample size, smaller margin of error. That's the takeaway. On to number 7. So Erica wants to predict if over 50% of seniors will vote. And she selects 140 of her classmates, and 51% say they will vote. All right. The associated margin of error is 2.5%. All right. Which of the following is accurate? So here's the deal. She's trying to predict if over 50%, but she gets 51% in her sample, right? But that's a 2.5% margin of error. So that means we could be 2.5% more than that or 2.5% less than that. So that means it's either 48.5%, between 48.5% and 53.5%. That's 2.5 in each direction. Well, that's not enough because we are pretty certain that it's between these two values, but that leaves open the possibility that it's less than 50%, right? Because less than 50% is in our kind of likely region here. All right. So therefore, we do not have enough information to say that they will vote to change the mascot. Now, if both of these numbers were above 50%, then we would say that we have sufficient information. There's no way we can say 51% will vote because, again, we're always just trying to make predictions about the population. Um, again, we don't know that they'll vote to change it because there's a high, there's a decent probability that it'll be less than 50%. And they will vote with at least 53.5. That's just kind of ridiculous. Okay, so it is definitely A. So anytime you want to know if something is over like a majority, right? Over 50%, then you need your margin of error to be completely above 50%. Like your low and high end have to be your interval has to be completely above 50%. All right, number 8. So, All right, so we kind of skim here. We want to know whether their library is more effective than home. They select a random sample of 200. That's great. But then so that's sampling, right? So then it looks like what we're doing is an experiment because there's 100 students. Um, they study at the library and 100 students study at home, and then they compare them, right? The problem with that, though, is that they were sampled randomly, but they weren't randomly assigned. All right. So there are other variables that could possibly be a reason um, for why those who studied at the library. Um, oh, they didn't even really say. It didn't even matter. Just how should this be changed? So it should be changed because we should do random assignment. All right. So that's important. You get a random sample, and then if you do an experiment, then you have to do random assignment within that experiment for the results to actually be more effective. Okay, on to number 9. All right, so now we get away from the whole like margin of error, sampling, random assignment, experiments, that whole part of it. And now we go into kind of what happens when we manipulate like mean, median, mode, range, standard deviation. All right, so the scores in 43 students were reported and they found out all this information. They made an error and the student with the highest score actually scored 8 points higher. Which of the following will not change? Well, the range is the highest minus the lowest. Well, the highest score, only the highest score, will actually be higher than it was, but the lowest score will still be what it was. So the range is going to change. Um, the mean is also going to change because you now have a different total, right? You've added 8 points to the total and you're still dividing by 43, so that's going to change. And the standard deviation is a measure of how spread out the data is. Well, you just really how far it is from the mean, but we can just think of it as a measure of spread. And this data is more spread out now because the highest person is even higher than they were. So that leaves median, and that makes sense. All right. So if you just think of an example, I'm going to do a much smaller example, but let me make this make sense, actually. So we're talking about the scores on an AP test. So let's say you just take some students, and these were the scores: a 2, a 3, a 4, and a 4. All right. So we can clearly see that the median, the middle number, is a 3. So then let's say this person jumps up to a 5. Well, that's not going to really affect the median at all, right? It's just going to move this one further away, but the middle number will still be the middle number. All right. So that's what they're talking about. All right. On to number 10. Math teacher increased his student scores by 12. Which of the following would increase after this change? Now, this is different than the one before because all of the student scores are going up by 12. So they're all shifting up together. So if everything shifts up by 12, then the mean and the median should both shift up by 12. The range will not because the highest value will go up by 12, but so will the lowest value. So when you subtract them, you will get the exact same answer. And same thing with standard deviation. Standard deviation is how spread out the data is, again, or like how far it is from the mean. But if everything shifts up together, then nothing is more spread out than it was before. So that's not going to change. So increasing it by 12, every value by 12 increases the mean and median by 12, but it will not change the range or standard deviation. So the answer is B. Okay, number 11. So what we're talking about here is median and standard deviation of a dot plot. And these both of these dot plots are symmetrical, right? So this one has like 1, then 4, then 2, then 3, then 2, then 4, then 1. Same thing here. It's like 2, then 4, then 2, then 1, then 2, then 4, then 2. So clearly the middle is the same. All right. So that's pretty easy to see. You could do your whole cross out method, or there's different ways to look at it, but these are symmetrical. So the median's literally going to just be the middle just by looking at it. If this were skewed one way or the other, then we wouldn't be able to say that. So I hope that's pretty obvious. So the this is true. All right. Now the standard deviation of A is equal to the standard deviation of B. Well, standard deviation is it's a loosely the measure of how spread out the data is, but what it really is, it's the average of how far the data points are from the middle. So the thing that's going to what goes, you don't need to know how to find standard deviation on the SAT, but you do kind of need to understand that the way that you find it is you subtract it from the mean and then you like square it and add it and divide it and square root it. So just know that however far a data point is from the mean, the further it is away, the more it's going to contribute to the overall value of standard deviation. So I just look at the ends and I say, well, this one is going to have four values that are really far away that are going to contribute greatly to this, where this one's only going to have two. And then it's going to have everything else the same. It's going to have the same number of 11s and 15s, the same number of 14s and 12s, and then it's going to have a bunch of 13s, which aren't going to contribute because they are the middle. So B is going to have these two values, these two dots here are the difference, and those are going to contribute more than these two. These two won't contribute at all. These will contribute greatly. So B is going to have a larger standard deviation. So the standard deviations definitely are not equal. So therefore, the answer is just one only. All right. On to our last problem. This one's pretty interesting. I'm curious if others find like a quicker way to do this. So basically, they give us a little bit of like a histogram in words. They say the first group has eight clients that's between 170 and 190. So let's go 170 to 190, that there's eight of them. And then there's 11 that are between 200 and 230, right? And then the last group, there's 21, and their monthly fee is between 240 and 300. If a new client who is charged a monthly fee of $250 is added to the third group, what will be the effect on the mean? So here's how something affects the mean. If and just imagine it. We're all familiar with our grades in school, and we're all like, when we get a test, we know whether it makes our grade go up or not. It's really, really easy. Whatever your current average is, if you take a test and get a higher grade than that, your average is going to go up. Now, how much? I don't know. It depends on how many other grades you've had, and it depends on how much that test was weighted. But bottom line is your grade will go up at least a little bit. If you do worse than your average, your grade will go down. And if you get the exact score of your average, if you have a 92 and you get a test that's a 92, your average will not change, right? I'm sure we're all well aware of that. So the only way that this will actually have an effect is if 250 is bigger than the mean, then it will increase the the mean. And if it's less than the mean, it'll decrease the mean. And if it is the mean, then it'll do nothing. Okay? That's these three answer choices. So, what we're going to do is we're going to try to figure out what the mean could be. But all we have are these ranges, right, for each group. All right? Um, so what we can do is just find two different means. Imagine that we had all the lowest values. So that would mean eight 170s and 11 200s and 21 240s. So what we would do is you could just do 8 times 170. Here, let me write it out. 8 times 170 plus 11 times 200 plus 21 times 240, right? And then we're going to divide that by 40 because 21 plus 11 plus 8 is 40. So there's 40 total clients. So I'm going to figure out this number. So 8 times 170 plus 11 times 200 plus 21 times 240. 8,600. And if I divide by 40, I get 215. So 215 is like the lowest possible that the mean could be. I imagine a scenario where all of these were at the lowest value. Now imagine that I do the highest value. All right. So that's going to be 8 times 190 plus 11 times 230 plus 21 times 300. And again, all over 40. So let's do that. 8 times 190 plus 11 times 230 plus 21 times 300. And if I divide that by 40, I get 258.75. Well, here's the thing. We know from this information is that the mean is definitely between those two values, but we don't know what. They didn't give us enough information. So that means when I add a value of 250, I don't know whether that will increase, decrease, or make the mean the same because we don't know exactly what the mean is. Now, if this range went up to like say 240 and we knew that this was greater than the mean, then we would know that we would have increased the mean or vice versa if it was less than the range. But since it's within the range, we don't know if adding 250 what it's going to do. So the answer ends up being D. There is just not enough information to determine how the mean will change. Okay, that is the end. So thank you for attending or watching on YouTube. Check out our TikTok. You're already maybe on YouTube. If not, check out our YouTube. We do offer one-on-one tutoring, call, text, email. We'll be doing some courses as well. We do a lot of stuff surrounding the SAT. But thanks for taking some time out and watching this, and I will see you next week.